In this lesson, we're going to talk about, we're going to try to put together all of our skills from algebra and calculus, all the way back from maybe 8th, 9th grade up to the present. And we're going to use all these skills to make an accurate picture of a function. So let's start with simple stuff like domain. I'm choosing to do, obviously you saw the PDF posted next to the video, I'm choosing to do a rational function because rational function will incorporate a flavor of every single thing that we have studied, and if you can do that one, then many of the other ones, such as polynomial functions, are actually a lot more simple. So let's do this rational function. It is 2x squared minus 9 over x squared minus 4. So there's our function. Just going to check to make sure you have a good view of it. It's a little bit on the small side. Okay, so we've got, this is our function, 2 times the quantity x squared minus 9 times x squared minus 4. The first thing we're going to do is study the domain. I'm a few pages into the PDF. You'll find that function if you just look through it. But the domain is basically going to be all real numbers except 2 and negative 2. You can tell that because of the denominator. The denominator will be 0 if that's 2 or negative 2, and therefore the function will be undefined, so we restrict them from the domain. Okay, now we're going to take the derivative. So let's do f prime and f double prime. I'm going to give you a second to do that for yourself, but the finished form, try to factor and cancel as much as you possibly can. Go ahead and take the derivative there. The first one should be 20x over x squared minus 4 squared. And the second derivative should be negative 20 3x squared plus 4 over x squared minus 4 cubed. Yeah. So now those are our two derivatives. I'm actually going to skip to the increasing, decreasing concavity part of the discussion now, because we've got our derivatives right here. So the first thing is I'm going to make little number lines. I'm going to decide on the first derivative what are values I should worry about. Before I even look at the first derivative, though, I know the domain, we have domain restrictions. So we need to worry about negative 2 and positive 2 already. Now we look at the first derivative, and we've already taken care of the denominator. We need to set the first derivative equal to 0 and solve. So give yourself a second to do that. And hopefully you've paused and done that now. Set the numerator equal to 0, and you'll find that x is 0. So the three values of our interest are negative 2, 0, and positive 2. And now we plug in values in these 1, 2, 3, 4 intervals into the first derivative and see whether or not it's positive or negative. Of course, if it's positive, that means the function is doing this, it's heading uphill. If the first derivative is negative, that means we're heading downhill. So when we substitute first of all, the denominator is going to be positive no matter what because it's something squared. Then we just have to figure out what the numerator's doing. So substitute a negative in here. You'll find that the function is decreasing. It continues to decrease as you substitute a value in between 0 and negative 2. And then the other two will be increasing and increasing. Now we go to the second derivative to see what's going on there. Notice the bottom is now cubed, so we cannot just look at it and say, well, of course, the bottom is always going to be positive or negative because that can change. The numerator, however, is different. The numerator, we've got a quadratic expression here, and that quadratic expression is always going to be positive, but there's a negative 20 here, so the numerator is always going to be negative. So let's first set this equal to 0 and solve. I'm putting 2 and negative 2 down here because they are, of course, restricted from our domain, and again, the denominator of the second derivative would reveal those to you if you set the denominator equal to 0. Also set the numerator equal to 0 and solve. So maybe pause right here and set that numerator equal to 0 to solve. I have a call while you're doing that. Hey, can I call you back? Thanks, bud. Sorry about that. So hopefully you have set the numerator equal to 0 and attempted to solve, only to find that it's not solvable. So the 3x squared plus 4, the problem here is 3x squared plus 4 is always positive, right? When you square something, multiply it by 3, you're staying positive, then you add 4 to it, that's positive. So that thing's never going to equal 0. So the only two values we have to worry about with the second derivative are negative 2 and 2, which we already identified as problem children in the domain. So now we substitute a negative in here, and you'll see the top is negative no matter what. The bottom, if you substitute negative 5 in, for example, the bottom becomes positive. So we are concave up there. And a little worried that I made a mistake. Oh, I'm sorry. I did. The bottom is positive. That was hasty. The bottom is positive as we substitute negative 5 in, but I already said the numerator the whole time will be negative, so that is my mistake. It's concave down. And then when we substitute 0 in, the numerator remains negative. The denominator, however, is negative as well, so it's concave up. And then I'll leave it to you to verify that after 2 it becomes concave down. Now, if we summarize these two pieces of information, by these two I mean the increasing, decreasing versus the concave up, concave down, I'm going to list all the values that I care about directly underneath where they're listed in the interval above. In other words, negative 2, 0, 2. Anything that's involved in the first or second derivative I put on my summary line. Now in the summary, I'm just looking for what's happening, decreasing down. So I'm just going to indicate it's decreasing concave down. The next one is decreasing up. The next one is increasing up. And then last, after 2, it's increasing down. Now these are it's a strange thing just to think about that in isolation, but something that's decreasing and concave down, just try to picture that. We've got 4 major shapes here. Decreasing and concave down is kind of like that, right? To be decreasing and concave up, you'd have to look like that. To be increasing and concave up, you'd have to look like that. And to be increasing and concave down, you'd have to look like that. So those 4 shapes somehow are going to define our graph. Now, we don't have locations yet, but you could see how we could fuse them together to kind of make a either continuous or discontinuous picture. So now we're going to solve for intercepts, asymptotes, etc. So the x-intercept, if we take our original equation and set it equal to 0, to find the x-intercepts, we would find that happens at 3, 0 and negative 3, 0 because of the numerator. The y-intercept is when x is 0, and you would get negative 18 over 4, which is 9/2, also known as 4.5. I'll list it as 9/2, whoops, inverted my x's and y's. I'll list it as 0, 9/2. Okay, those are ideas going all the way back to Algebra 1, maybe even pre-algebra solving for x-intercepts, y-intercepts. Now we're going to look at vertical asymptotes. This would go to a pre-calculus course. Vertical asymptotes. If you go in to find when the denominator equals 0 but the numerator does not, you'll find vertical asymptotes at x equals 2 and x equals -2. Right? That's when the denominator equals 0. Notice I said the denominator equals 0 but the numerator does not. Just a question to pose to you is, what happens when you substitute a number in for x and it makes the denominator 0 and the numerator 0? So maybe take a second to think about that, maybe come up with a function that does it, but it's definitely something you've seen before and something that you'll see again. So we've got our vertical asymptotes. Last thing is the horizontal asymptotes. And to do those, we need to do the limit as x approaches infinity of the function. And if you go back to this function and you let x approach infinity, what I'm going to do first is distribute. If we let x approach infinity in this function, the numerator and denominator are codominant. In other words, their degrees are the same. So we actually take the ratio of the coefficients of the leading terms. So we find this limit to be 2. I want to make sure you can see that on the right side. Yes. Okay. And then if we do the same thing to find what happens when x approaches -infinity, we find it's also 2, and that's because of the square. So why, just to recap there, why did we do the limit as x approaches infinity and -infinity? Well, at -infinity, we're seeing what happens all the way at the end of the function. And at positive infinity, we're seeing all the way what happens at the end of the function. If there were horizontal asymptotes to be found, that's the only place they can be. So now we've basically, I left end behavior on that PDF, but we just sort of described the end behavior on the right side, and on the left side it goes to 2. So now I'm going to make a picture. Okay, things that are totally not dependent on shape and etc. are x-intercepts, y-intercepts, and asymptotes. So I'm going to put my asymptotes on here. First asymptote, vertical ones are x equals 2 and x equals -2. And the horizontal asymptote is at x equals 2. So we've got sort of, we're already bounded by all these asymptotes. Obviously we can't cross them, them being asymptotes. And then I'm going to start my graph in red here, and I've got the x-intercepts at 3, 0 and -3, 0. So I've got 3, 0, -3, 0, and the y-intercept is at 4.5. And now is when our shapes come in. And these 4 shapes must fit within the confines of the asymptotes and the intercepts. The first one is decreasing concave down. You can see very clearly how that would make sense. The second one is decreasing concave up. Notice I'm decreasing. You might think, well, isn't it going up? But not as you go from left to right. It's actually going down. After that, at 0, it begins to increase and be concave up. And then after that, it's increasing in concave down. So there you have it. Everything that we've done in calculus to this point basically is encompassed in this. But the really cool part is also it allows you to pull together really years of studying math. Just to take a look at everything we've done, we've found x-intercepts and y-intercepts, a pretty elementary concept relative to the rest of the things we're studying now. We've determined domains, something you've been studying for a long time. We took 2 derivatives, and we used the derivatives to tell us when things were increasing, decreasing, concave up and down, and then we've summarized them with a graph after finding horizontal and vertical asymptotes. There's really a lot going on here.